In our lessons so far, we have seen how the concepts of arrays and pointers go together. Now in this lesson we are going to talk about character arrays, how we can work with character arrays using pointers. When we talk about character arrays in C, we basically want to talk about strings. Strings are a group or set of characters, and real world data like names, phrases and sentences, all of these are strings to us. So these are some of the examples of strings. Character arrays become all the more important because we use them to store strings and then perform a lot of operations on strings, like modifying a string, copying a string, concatenating two strings, or finding out properties of strings like finding out the length of a string. To be able to work with strings efficiently in C, there are a couple of things that we need to understand. The first thing that we need to understand is how we store strings in character arrays. To be able to store a string in a character array, the first requirement is that the character array should be large enough to accommodate the string. And what is a large enough character array? A large enough character array is a character array of size greater than or equal to number of characters in the string plus 1. So let's say if our string is a name of 4 characters like John, then the size of the array should be greater than or equal to 5. Now the obvious question would be, why do we need space for one extra character? Isn't it that if we declare a character array of size 4, we can store all the characters in John? J will go at the 0th index, O will go at the 1th index, H and N will go at 2nd and 3rd index respectively. So I'm storing all the data, isn't it? Let's try to understand it this way. Let's say we have a character array of size 8. Let's say this is a logical view of our array C, and we want to store the string John in this particular array. We have indices from 0 to 7, and this is an array of size 8. So we can store J at the 0th index, O at the 1th index, H at the 2th index, and N at the 3rd index. So we have stored all the characters of the string John in this array, but if you see, we have not stored one information. We have not stored the information that this particular character N is the last character in the string. So the string ends at index 3. So let's say if we pass this string to a function that has to print the string John or find out the length of the string that we have stored in this array, then how would the function know that the string is only till index 3, even though we have not filled anything in these indices at 4, 5, 6 and 7? There would be some garbage value there. So either we pass this extra information or we do something else. To store this information that this is the end of the string in the character array, this is the used part of the string and this is the unused part, we use a simple design. At the end of the string, in the next position, we put a null character. A null character has ASCII value 0, and we can put a null character at position 4 in this example, something like this. Within single quotes we put a forward slash and number 0. This is null character. All the functions for string manipulation in C expect that strings will be null terminated. So this is a rule. A string in C has to be terminated by a null character, and that's why we need one extra space to store this null character. Let us try to see some running code that will help us understand this concept better. What I have done here is I have taken a character array of size 4 and I have filled in the characters, but I have not used any space to null terminate it. And then I am using the printf function. This %s here tells that I want to print a string, and then I'm passing this array C. Let us run this program and see what happens. As we can see, there are these bunch of characters that are getting printed after John. And this is happening because we have broken the assumption for the printf function that my string, that our string will be null terminated. So that's why this undefined behavior is coming. If we change the size of the character array to 5 and put a null termination, something like this, at 4th index, then things will be fine. Now even if we change the size of the array to 20, printf function will print till it finds a null character. so it only prints the first 4 characters in the array. And it's not just the print function, there are a bunch of functions. We have this library string.h that gives us a bunch of function for string manipulation. So all these functions assume that the string will be null terminated. So this is one contract that we have to follow. Let's say we want to use one function strlen string length to find out the length of the string. I'll print something like this. Let's run this and see. As you can see, the output is length is equal to 4, even though the array is of size 20. So string length function also counts till it sees a null character. In our program, instead of writing these characters individually at these positions, we could have used string literals. String literals are a group of characters within double quotation mark. So we could have written something like this, and this would have initialized C as this string, and the null termination for a string literal is implicit. It is always stored with a null termination in memory. Remember, when we declare and initialize a character array like this has to happen in one line. We cannot do something like we declare in one line and then we go on and modify this in the next line. This will be invalid. We could also avoid writing this size here, and this would have been fine. In this case, the size of C will be 5 units, 5 bytes, where 1 byte stores 1 character. So it would be just enough to store this string John. So if we try to print the size in bytes of C using this size of function, then size in bytes is 5. 1 character is stored in 1 byte, so space has been allocated for 5 characters, but the length is 4 because the null character does not count in the length. If we write something like C4 is equal to this particular string literal with 4 characters, this will give us compilation error because the compiler will force this particular array to be of minimum size 5. There is one more syntax of initialization. We can put all these characters as a comma separated list within these braces, but in this case the null termination will not be implicit. We will have to do it explicitly, and the size of the array has to be greater than or equal to the number of characters here, so it should be greater than or equal to 5. Okay, so these are some of the ways to initialize character array. The next thing that we need to understand is arrays and pointers are different types that are used in similar manner. Now, what does it really mean? Let's say we declare a character array C1 of size 6 and initialize it with this string literal, and let's say this is how it gets stored in the memory. Array is stored in one contiguous block of memory. So let's say the first character is at address 200. One character is of size 1 byte, so the next character will be at address 201, and the next will be at 202, and so on. Now C1 is the variable name for this whole array. Now what I'll do is I'll declare a variable which is a pointer to character. Let's name this C2. So let's say we get this variable C2 somewhere in the memory. A pointer variable in a typical architecture is stored in 4 bytes. So this variable will also have some address. Let's say this variable is at address 400. I'm just picking up these numbers for example's sake. Now what we can do is we can write a statement like this: C2 is equal to C1. Now even though C1 is a character array, is a variable name for character array, and C2 is a variable which is pointer to character, this particular expression is valid. Just using the name of the array actually returns the address of the first element in the array. So what this statement will do is it will fill in the address 200 in C2. So C2 now points to the first element in the array. Now we can use this variable C2, which is a character pointer, just like C1, to read and write into the array. So if I write something like print C2I, let's say we want to print C2 1, then the output will be L, and we can even modify the array. Let's say we want to modify the character at 0th index to A. So the string will be modified and will become this. When we write C2I for any position I, it is nothing but asterisk C2 plus I. So C2 is the base address. C2 plus I will take you to the address of the ith element. So in this case, let's say C2 plus 2 will be 202, and if we put this asterisk operator, we are basically dereferencing and finding out the value. So these two syntaxes are alternate syntaxes, and even if it is an array name, we can write these two as substitutes for each other. So this was all the similarity in how we actually use arrays and pointers to read and write. Let us now look at the differences. We cannot modify an array with a statement like this. C2 equals C1 is valid, but C1 equals C2 is not valid. It does not make sense. This will give you compilation error. We cannot even say C1 is equal to C1 plus 1. We cannot increment or decrement this variable C1. We can do it for C2, which is a pointer variable. We can say C2 plus plus. So C2 now points to the next element. With this statement here, all that will happen is C2 will become 201. So instead of pointing here, it's now pointing to this particular element E. To traverse an array, we run a loop and we use a local variable, let's say I, and increment it in the loop. If we have a pointer variable, we can just keep on incrementing the pointer and we can traverse the list. We can traverse the array. We will keep doing this C2 plus plus. So we must understand where we have an array and where we have a pointer and what we can do with which one. Now the next thing that we need to understand is that arrays are always passed to functions by reference. When we pass arrays to functions, we only pass the base address of the array in a pointer variable, and we do not pass a whole copy of the array. The compiler does not let you do that. We have talked about this in detail in our previous lesson, arrays as function arguments. Let us look through some code and try to understand this better. In my code, I have declared a character array of size 20, and I have stored a string of length 5 in this character array. The null termination is implicit if we are using string literal. Now I want to print this string, but I do not want to use the library function printf. I want to write my own function print. I want to pass this array to the function, and this function should print the string part in a character array. The argument to the function, we have talked about this earlier, can be something like this to say that we are receiving an array here, but the compiler actually interprets this as this. So the compiler forces that only the address of the character array or the address of any array be received as argument to the function. Because arrays are large in size, so it is inefficient to create a copy of the same array for each function. Okay, so let's write the logic now. Now this print function does not have any idea that this particular array is of size 20. It only knows the base address. So what we can do is we can have a variable I, initialize it to 0, and we can say something like this: while ci is not equal to null character, we can print the character ci, and then we will increment I, and when we find a null character, we can come out of this loop and print an end of line. Once again, this print function does not know that this character array is of size 20. It only knows the base address, and that's why in the printf function, when we were not null terminating an array, we were printing all the garbage value even after the array was finished, because until we get a null character, we do not know where to stop, and we keep on going into unwanted memory locations. Now this code should work. Yes, this is fine. In my code here, I am using %c here to say that we want to print character, and ci, we can also write asterisk c plus I as substitute for ci, and that will also mean the same. Sometimes you'll see this kind of syntax. As we talked earlier, both of these syntax, asterisk c plus I and ci, are valid. They're the same. There is one more thing in our code that we may do. We may not choose to have this particular variable I. We could simply say that while asterisk c is not equal to null, print asterisk c and then increment c itself, and this code will also work. Why this code will work, I'll leave it as an exercise for you to think. In the coming lessons, we will implement more functions for string manipulation. This is it for now. Thanks for watching.